All right, welcome back for another episode of Connie 352 Mechanical Systems. Today we're going to be discussing R values and calculating the total resistance to heat transfer for things like walls and roofs and that sort of thing. For this lecture, you're going to need a few things. All right, so if you need to pause and go get them, that's fine. Obviously, I won't know if you do. Go get from Canvas. Right, you need to get the notes packet. Notes packet, section 1, HVAC. And by the way, this is easiest if you just go to the home page on our Canvas page, right? The HVAC module, all right? You need the notes packet. You need the PowerPoint that's HVAC02, R values and U values. And then you need this last one, which is the HVAC calc handout. So go and get all three of those. You may find it handy to print out that last one, the HVAC calc handout. You're going to need this for both R values, but also cooling calculations, heating calculations. You're going to need it for all of them. So you might want to print it out. It's just kind of handy if you highlight some of the important things in there. So go ahead and do that. And once you have all of those things, we are going to get started. All right, so let's start with the PowerPoint on R values and U values. So what is an R value? When we go to calculate heat transfer across the wall, the equation from that is if Q is the total heat transfer across the wall in BTU per hour, to calculate that, I need to multiply that times a U factor, the area, and then the difference in temperature from inside to outside of that wall assembly. Well, let's talk about the components of that. We'll talk more on this equation tomorrow and Monday as we look at heat transfer. We do some heat transfer calculations. But a U factor is the inverse of an R value. If you buy a window, it's going to come specified with an assembly U value. It'll probably be on a sticker in the middle of it. If you go to Menards or Lowe's or Home Depot and you look at windows, you're going to find a sticker with a kind of a performance tag on it, and it's going to tell you what the U value is for those items. Now, an R value is how if we're looking at not an assembly like a window comes all together, but a wall, you're going to build with individual components. So if you're going to do that, you need to have the R values of the individual items and you add them up, and then you take the inverse to get the U value. All right, let me give you an example. If we're looking at a wall and you go to buy some insulation, maybe you buy the rigid pink insulation and it has a certain R value, probably pretty high per inch of thickness. Or you could get something cheaper like a batt insulation that you roll out, and there's various quality levels. The greater the R value, the better that material is at stopping heat transfer. So you want to get, if you're getting insulation, the higher the R value, the better, the less heat loss. All right. Now, the area of the assembly is not like a cross-sectional area, but if you're looking at that wall, it is the square footage that separates the inside from the outside. All right. So what is that? The height and the length of that wall, that is the area. And then the difference in temperature is the difference from inside to outside of the wall assembly. So we're going to talk more about heat transfer, like I said, on Thursday and then Monday. But for right now, all we're worried about is getting this R value, the composite R value for a wall. All right. Now, the total R value is the sum of its components from inside to outside. I mean, it doesn't matter if you're going from outside to inside or inside to outside, but they are in series, right? And we're going to look at some tables. Those tables come from this handout. that I printed off and uploaded. That's that HVAC handout page, the last item that I was telling you about. So we're going to come back to these tables. They're from the book. We're going to come back to them in just a second. What we're going to look at first is we're going to look at a brick and a block wall. All right, so this is like a standard brick and block wall. Every school in Iowa is probably made this way, where we have some type of a brick veneer, probably a face brick, not solid, meant to be more in appearance than it is load-bearing. There is, over here you see this, there is an air gap, probably at least an inch, maybe 2. That's where the moisture that gets through the brick is directed down to the weep holes. We learned about that in Connie 241. Past the air gap is probably some type of rigid styrofoam insulation. And then beyond that, that's where we have the concrete masonry unit, also known as the block. This is the standard school detail that has been used in hundreds, if not thousands, of school buildings across the state and across the country for that matter. If we look back in time, though, if we go back, say, a school maybe built in the 1970s or prior, the only difference is it's probably going to be brick and block, but probably not going to have that insulation in the middle. And we're going to look at both of those, because if you go to remodel an existing building, not having that insulation is pretty important. And it definitely affects your building. So I want to come back and talk about that insulation and what it does for us. All right, so what we do with that brick and block wall is that we need to add up all of the different R values. And this is the point. This is the point at which we're going to do that for the one with insulation, the one without insulation. But what I'd like to do is turn to that handout. Let's turn to that handout and just take a look at it. And let me kind of walk you through it. So grab the handout. Like I said, you might want to print it out. This is taken from the textbook that I used to use. Not a great textbook. But it did have some tables in it that were pretty handy. And that's what this is. I printed out the tables. I put them in the order that we're going to need them, not the chronological order from the books. You'll notice it starts at page 64, and then it'll jump to page 41 or whatever. It'll jump around in page number a lot. But I put them in the order that we need them. The first thing that we need is to get the thermal properties of some typical building insulating materials. Right, so there's the description on the left, the density in pounds per cubic foot. That's not that important in this class. And then the important part is the last 2 columns, the resistance. The resistance to heat transfer, the R value. Either it is going to be listed in thickness per inch. That's the second column from the right. Or for the thickness listed. That's the very far right column. It's important to know that most of the insulating materials, they're going to give it to you in the thickness, in per inch. In other words, if I bought styrofoam insulation or I bought bad insulation, did I buy 1 inch, 2 inch, 4 inches, 6 inches of it, whatever that is? So they'll just give you the thickness per inch, and then you've got to multiply it out. For masonry units, that type of thing, this is a 4-inch brick. This is a 6-inch block, something along those lines. They're just gonna give you the R value for the thickness listed. All right. So some of the more important ones that we're gonna need in here. If I say insulation, batt insulation, go down to where it says, all right, so there's building boards. Let's start there. That's where we find gypsum or plasterboard, right? Let's see here. Right here, 1/2 inch. So it lists it as a 1/2 inch gyp board. So the R value is over there on the right. All right. Going down, let's see. Oh, you might, like on an exterior of a wood wall, you might have a, let's see here, probably plywood, like a Douglas fir plywood. That's fine to use. It gives it to you in thickness per inch. That's at 1.25. But also it listed at 1/4 inch plywood, 1/2 inch plywood. So if I gave you something that wasn't that exact dimension, you could use the thickness per inch and multiply it out. All right. Let's go down to boards and slabs under insulating materials. Under insulating materials, like a cellular glass, if I say bat insulation, that is going to be the cellular glass. If I say rigid insulation, right, that is going to be this, the expanded polystyrene. Those are some common insulating materials that you're going to see in industry, but also in this particular class. Okay, let's go to the second page of this handout. Roofing, a common roofing insulation is this one. Cellular polyisocyanurate. Has a good R value, but also it's more durable. In other words, we're worried about people walking on it for like a low-sloped roof, or perhaps hail and wind and that type of thing. So common roofing insulation is that polyisocyanurate. Let's go down to, here we go, masonry units. And the very bottom, common brick and face brick. Most of the time, if a brick is a veneer, it's probably the face brick, that 0.11. And notice that is the thickness per inch. So if you have a 4-inch face brick, you multiply it by 4. Other common masonry units, let's go to the next page, where we've got concrete blocks. Notice there's a couple choices. All right, concrete block. The choice that you should use on this table is there's a choice between sand and gravel aggregate and cinder aggregates. Choose the sand and gravel aggregate. Very rarely are modern block going to be made with a cinder aggregate. There's also woods. Okay, you might need those, especially if we're talking about a wood frame wall that we're looking at. Okay, that's by and large the majority of the R values that you're going to use. A couple of other tables that are important here. Turn to the page. Let's see, the top of it, it says page 34, but the important part here is if you look at table 2.9, outdoor air requirements for ventilation. Later in the semester, when we look at, when we do our total heating and total cooling loads, we're going to need to know how much heat transfer that we're going to have because of the fresh air that we bring into the building on purpose. All right, the fresh air that we bring in on purpose. All right, let's keep turning. Some other things that we are going to need. Most of these, the rest of them are shading coefficients. See here, infiltration rates, shading coefficients. We'll talk about those when we get to cooling calculations. All right, so now let's switch back. Let's switch back to one of our files, but this time let's go to the notes page. All right, the mechanical notes packet. I'm going to use that to kind of go through the examples. I've got the example problems all written out in those, and that's what we'll follow along with. So go down to page where it starts with R values and U values. Okay? In addition to the physical materials like the wood, the brick, the block, the insulation, and there's a couple of other R values that we're going to have to account for. That air gap in the block wall between the brick and the insulation, I've just simplified one of those tables. All right, use this. For air gaps, use an R value of 1. All right, an R value of 1. That's all I want you to use. No matter what the thickness is, tests have shown that an R value of 1 the R value of an air gap of 1 inch is about the same as it is 2 inch and about the same as it is 3 inch. What happens is, even though you expand that air gap a little bit, it becomes large enough that you'll get some air currents going through there and actually transfer energy just as good as if you had a smaller air gap. So adding a wider air gap within the wall itself doesn't do anything to help. For the R value at the wall itself, there is an inside surface resistance and an outside surface resistance. I didn't print out table 2.5 because I basically tell you just to use these values. The inside surface resistance, there's actually an air film that kind of clings to the inside surface of a wall and the outside surface of a wall. It's called the laminar boundary layer as you get right up to the wall, and it does have a little bit of an R value to it. The inside surface resistance, I want you to use an R value of 0.7. I'm going to simplify table 2.5. I didn't even print it out. I want you to use an R value of 0.7 for the inside surface resistance, and then an R value of, right here, this is on this diagram. Here's that inside surface resistance and the outside surface resistance. On the inside, I want you to use an R value of 0.7. On the outside, I want you to use an R value of 0.2. On your handout, it looks like that 2 got replaced by something it shouldn't have. Right? So the inside surface resistance is 0.7. And the outside is 0.2. And the reason being is that usually the inside air surface the air is relatively still. And on the outside, there's probably some wind or breeze, and that cuts down the resistance to heat transfer. All right, so what we're going to do is we're going to add up all of those R values to get the R value of the wall. First, I'm going to do it with the brick and block. I'm on page 7 of the handout. We're just going to do it very simply. Brick, block, air gap, and then there's no insulation. This is the old elementary school wall from the 1950s. And notice, as we add up these values, okay, this is how I want you to do it for your homework. It's how I want you to do it for the final project. Go from outside to inside and just add them up. List them. I want to see this. So the outside air film has a resistance of 0.2. The brick itself has an R value of 0.44. You take, right, that R value of 0.11 per inch that we looked up in this table. If you go down to the very last, on the second page of the handout, go down to the very last entry. It says brick, comma, face, has an R value of 0.11 per inch. So then you multiply it by a 4-inch face brick. Next is the air gap. Okay, air gap right here. It's a 1-inch air gap. Even if it was a 2-inch or a 3-inch air gap, we're going to give it an R value of 1. Next is the 8-inch CMU, concrete masonry unit. Don't forget to use the sand and gravel aggregate concrete masonry unit. has an R value of 1.11, and then the inside air film of 0.7. We add all those up, and we get an R value of exactly 3.45, which, in terms of the R value and energy performance of a wall, is not very good, to be honest. It's not. When schools were built in the 1970s and prior, it was all about first cost. Insulation was very expensive, and they didn't cool buildings anyway then. They opened the windows if it was too hot. And in the winter, all they did is if it was too cold, they had a boiler and they shoveled more coal. That's all there is to it. They didn't put a whole lot of emphasis on energy efficiency. So another important thing to understand is sometimes I've had students ask, it's like, why even consider the R value of the air? I mean, isn't that negligible? All right, it's 0.2 on the outside, it's 0.7 on the inside, it's only an R value of 1 in the center. Well, it may be negligible, but for this particular wall, if we add those up, that's 1.9. That's over half of the total R value for the entire wall. So you might be talking about an older building where that R value for the air gap and the air films is fairly significant. Now, on a modern building, if we go down to the next example where we've added a 2-inch rigid insulation in the middle, 2-inch of expanded polystyrene, it's the exact same wall, it's the exact same calculation, it's just that 2 inches of poly gives you, at an R value of 4 per inch, it gives you an R value of 8, and now our total is 11.45. Yeah, you could say now, okay, in this wall, maybe that R value of the air is getting kind of negligible, but it's still worth including. It's still worth adding. Now, let's make a judgment here on this R value of 11.45. That would be, for a modern building, just barely code minimum. All right, just barely. It's not a very good wall in terms of energy efficiency. A better wall assembly would be a total R value of somewhere between 16 and 20. All right, that would start to get a little bit better. A really high performing wall would be over 20. The thing you have to know, though, is once you get above an R value of 20 for a wall, we start getting to the point of diminishing returns. In other words, if I increase the R value of the insulation in this wall, what does it cost me versus how much energy does it save? And I think what you'll find when we start doing total heat transfer calculations a little bit later in the semester, you'll find that the R value of the wall isn't near as important as some other things. And those other things would be things like, well, what glass did I buy? Glass is incredibly important when it comes to energy efficiency of a building. What equipment, like chillers, boilers, air handlers, what equipment did I buy? What lighting systems did I buy? Those are all far more important than increasing the R value of the wall. All right, so let's continue. Okay, so here's kind of a cut section, kind of an example, brick block insulation air gap again. Very, very, very similar to the other drawing that we are looking at. Now, let's see here. Since we're talking about brick, you can tell when that cavity is interrupted, as we were talking about in Connie 241. I have a couple of pictures of brick structures with efflorescence, which means there's probably something wrong with the air gap, something wrong with how moisture is getting out, perhaps something wrong with the weep holes or the flashing. And all of these are just pictures of efflorescence. Right? Here's the temperature profile. Now, something else, something very important that we can look at and calculate using the information that we have with the R values. If we know the inside air temperature and the outside air temperature, we can actually calculate the temperature at each interface and at any point in this wall. The temperature is going to change in proportion to the R value of the item it's going through. For example, something like steel, like let's say that those were steel studs here, has a very, very, very low R value. There's almost no temperature difference across that. However, something like this, with a very steep profile, that's an insulation or something that has an insulating value. And you're going to have a much greater temperature change as you go from inside to outside. The slope of this curve is proportional to the R value of the item that it's going through. And what that will do is that allows us, is something very important, it allows us to calculate the temperature, and we can do that at each interface. And this is actually a homework problem. The way you do this, all right, figure up the outside and the inside air temperature difference. On the example that I have here, it's minus 10 degrees outside, it's 70 degrees on the inside. The difference in temperature across that wall is 80 degrees Fahrenheit. This brick and block wall had a total R value of 3.45. So the way to figure out the temperature at each air gap is to first figure out for every one R value, how many degrees does it change? You just divide the total difference in temperature by the total R value for the wall. In this case, and I apologize, this number is wrong, but these values are correct. All right, that should be 3.45. Let me just fix that. We divide that out, and it ends up being 23.2. What that means is we can figure up the temperature at each interface. If we start at the inside wall, we're starting here, the temperature at the surface is going to be 70, that's the inside air temperature, minus the R value of the air film, that's the 0.7, times the ratio of degrees Fahrenheit per R value of 23.2. So the temperature at this surface is 53.8 degrees. Next, we're going to do exactly the same thing. We're going to keep going from inside to outside. So at the wall, it's 53.8 degrees. So if I want to find out what the temperature is at the block, I start at 53.8, that's the temperature we just found, minus 1.11, that's the R value of the block, times 23.2, and that gets us to 28.048. Normally, in this class, don't get too worked up about how many decimal points that you have, but in this case, it helps if you do like 3 significant digits past the decimal. That should be loads of plenty. All right. So at the brick, all right, I'm sorry, at the other edge of this block, it's at 28.048. All right, now let's go from the block across the air gap. Going across the air gap, I start at 28.048. I go across the air gap. The air gap has an R value of 1 times 23.2, and that takes me down to 4.848 degrees Fahrenheit. Next, I need to find the surface temperature here at the outside of the brick. So I start at 4.848 degrees here. I go across the brick that has an R value of 0.44. Multiply that by 23.2. The surface here is a negative 5.4 degrees. And if we've done this right, as I go across the air gap for the outside, that 0.2 air gap, R value right there, I should be right at negative 10 degrees for the average outside air temperature. All right, what does this process do for us? Knowing the temperature at each interface can tell us, here later in the semester, we're going to learn about dew point temperature. It can tell us where it's going to condense. That can tell us, where do I put the moisture barrier, or the vapor barrier, I should say, in this wall. Can also tell us when freezing is going to occur, right? Notice that freezing in this wall, freezing occurs within the block itself. If it's 53 degrees here and 28 degrees here, freezing is going to occur within the block. What that means is if there's any moisture in our wall, it could actually freeze within the wall itself. All right. Let's do the same thing. I'm not going to go through every step. I want you to review this. I'm not going to go through every step, but I want you to review this and notice that once we add this 2 inches of insulation, it changes this ratio and it drastically changes the temperatures at all of the interfaces. In other words, let's just look at the inside wall temperature. On the insulated wall, it's 65 degrees here. On the uninsulated wall, it's 53.8 degrees here. And that tells us something very important. If you've ever wondered on a wall, it's like, I wonder if it was properly insulated. I wonder if it was built properly. This is normally you'd have to drill through this wall to actually find out. By doing a little bit of algebra, we can figure out if this wall was built properly or not, and we can just measure the surface temperature of this wall. On an uninsulated wall, the surface temperature is much colder, right? That's a 12 degree difference in temperature. Had this happen where I used this on some precast wall sections that were supposed to come from the factory, insulated in the sandwich, kind of like the DMAC walls were, like a sandwich panel. And we had one room that couldn't keep temperature, and the question was, I wonder if it was insulated at the factory or not. Well, they were talking about drilling through it to find out, but a simple temperature scan told us whether or not any of these panels were uninsulated, and there actually was one. So being able to do this math, also something else important, notice these temperatures. So it's 65 degrees there, it's 57 degrees here, and then it's 1 degree over here. In other words, in this wall, this block is never subjected to freezing, at least at minus 10 degrees, right? In other words, we have moved the point of condensation outward, and we've moved the point of freezing outward. Insulation, not only does it save you energy, but it changes where that dew point and where the point of freezing is within your wall itself. And those are important things to know. All right. Now, what if this isn't a completely homogeneous wall? I mean, each item through the profile is the exact same. For wood studs and steel studs, we run into a little bit of a problem, but it's actually pretty easily analyzed. Notice this. Go down just a little bit. Go to page 14. So what a wood wall does is basically it's like two different walls, where we have one path through here goes through the sheathing, the insulation, and the drywall, and another path through here goes through the sheathing, the wood, and the drywall. And it's pretty common in a residential wood stud wall. Almost 15% of this wall can be assumed to be a wood wall, solid wood through there. And then only 85% of it is actually insulation. So what we'll do when we do the heat transfer calculation, you just figure up the R value through the insulation, and then do that as a composite wall, do the R value through the wood, and then whatever that total area is, let's say this was 100 square feet of wall, then 15 square feet of it is actually wood stud, and 85 square feet of it is insulation. And then you can do the heat transfer that way. Steel studs are a little bit different. Steel studs are very, very, very thin, but the steel stud itself has almost zero heat transfer. Zero resistance to heat transfer. Steel studs are essentially a thermal short circuit. The way to handle steel studs is, let's see here. Oh, okay, it's back here. The way to handle steel studs is here on page 13. Whatever the steel studs surround, and by surround I mean if we go to this picture, let's say that these were the steel studs. This insulation here that's in between the steel studs is short-circuited by the steel. What that means is we need to discount whatever this R value is. We need to reduce it by a factor of 60%. In other words, the insulation that is between the steel studs now goes from an R value, if it was an R value of 10, now it's an R value of 4. And you might think that that sounds like a very severe discount, but this has actually been proven. And maybe at my former firm, an engineer has made a mistake of not taking into account the steel studs as a short circuit thermodynamically. Remember though, it's only the parts that are between the studs. All right? That's the only part that's short circuited, this insulation. The drywall goes across it, so it's not short-circuited. The sheathing on the outside goes across it, so it's not short-circuited. It's only the stuff that is between the studs. And yes, that is a very, very, very real effect. Basically, what that tells you is, if you're putting insulation between steel studs, you are wasting 60% of that insulation. It's actually a terrible place to put insulation. And I know most contractors will see that void space and they'll think, oh man, that just seems wrong not to put some type of insulation there. Well, you're actually not doing a whole lot of good putting insulation there. So just keep that just remember that for future use. All right. I think we're gonna pause there. Tomorrow we're gonna talk about indoor environmental quality, and we're going to get into the heat transfer calculations. Remember, the labs in this class are really a little bit of extra time for case studies. I don't know if I'll get to a case study tomorrow, right? But we will have another lecture tomorrow, and I'll probably assign the first homework tomorrow. So keep up on the labs. Make sure that you have all these handouts, and look for another lecture posted on Thursday. Thank you.